Okay, so this is now week number 9, and we are in lecture 17. So I'm going to, today will be a short day because I have to leave early, but we're going to review quickly the 4 chapters that are going to be on the exam. So that's 8 and then 15 through 18. Is this a game to you? Pretty much. That will be accurate. So not really. Okay, so chapter 8. Chapter 8 starts with the difference between a excuse me, the difference between a population and a sample. All right. A population, of course, is the entire body of individuals that you are investigating. When I say individuals, I don't necessarily mean people, but it could be any group of objects that you're taking data from, and you have the population, and then you take a small portion of that, which is called your sample. How you take your sample is called your sampling design. And your sampling design is the method by which you take your sample. Okay. Hold on one second, everyone. I got to check one thing quick, and then we will continue in earnest. Okay. Okay. So let's go. Okay. So let's see what we have here. Again, we're just going through it quickly. So the sampling design is the method by which you take your sample. So we certainly had some bad samples or bad sampling designs. A convenient sample is certainly a bad sample because it didn't let it's not random enough. Okay, it's a sample by convenience. It can have a lot of bias to it because you're asking people at a Lakers game what their favorite sport is, right? It's convenient to do that because you're there anyways, but there's a lot of bias in it. Another one that's really bad is a voluntary response sample. Voluntary response are the people who want to respond, do so. And those people are usually ones who feel very strongly about the issue. And because of that, it's not representative of the entire population. The best is a simple random sample. We talked about this. Of course, this is a review. A simple random sample is a sample from a collection from the population chosen in such a way that any size sample or any sample of that size is as equally likely to be chosen as any other sample of that size. So if I'm picking 5 people from 100 and I do one from there, 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 that is not a simple random sample because there's no way that 5 people in the same area would be chosen. Okay, if it's truly a simple random sample, any 5 should be as equally likely to be chosen as any other 5. Human beings cannot do a true simple random sample. It must be done by computers or by picking names out of a hat or something like that. Okay, random digits is another way of creating a simple random sample because the random digits are purely random. We talked about that. It's a wonderful way of getting a simple random sample. Okay, and then of course the whole idea is to take inferences about design. You basically or inference about the population. You basically say, okay, I have this sample. Here's my data from the sample. How does that data from the sample extrapolate to the entire population? I want to conclude things about the entire population from the sample itself. And sometimes you can do that and sometimes you can't do that. When can you do that? When it's a good sample, usually an SRS. Most of our formulas later require an SRS. What are some other sampling designs? We had a stratified random sample where basically you break up the population into groups called strata and then take a simple random sample from each one. And then we combine them together to form the full sample. Like, for example, if I split up men and women and then take a simple random sample of each, or I split them into age groups and take a simple random sample of each. That's a stratified random sample. Something similar is called a cluster sample, where you break it up into groups, but rather than taking some from each group, you just pick some of the groups. So I might divide up a class of 100 into 20 groups of 5, and then pick randomly 3 of those groups of 5. So I'm not taking from each group, I'm taking 3 groups in there entirely. That's a cluster sample. We also had, let's see, that's it for this one. Sample surveys can be problematic. You can have a situation of under coverage where you don't include everyone who you want to include. It can be non-response problem where people just don't answer. Hey, don't call me here, and they hang up. Surveys are bad in general, especially because the wording of questions, or even who's asking the question. I was tutoring a kid the other week, and there was a question about whether the question was phrased to African Americans about whether or not they feel bias or hatred or animosity toward white people, and they were different answers if the interviewer was white or himself was black, because there was interviewer bias. The interviewer himself created bias in the problem. So not only the wording, but even just the person themselves can be problematic. So surveys in general can be very, very difficult to do well, and you should be aware of that. Impact of technology, I think we kind of skipped this section because, you know, I don't even know what they're talking about. So don't worry about that one. So then we went to 15. And we talked about the difference between a parameter and a statistic. A parameter is some number that describes the entire population, where a statistic is a number that describes the sample. So usually for a population, you'll have the mean, the average of the population. We don't know that, but whatever it is, it's a parameter. Or the number of people in the population is a parameter because it's a number that describes the population. Whereas something that describes the statistic would then be, something that describes the sample would then be a statistic. So the number in the sample, statistic. The average of the sample, statistic. The standard deviation of the sample, statistic. Okay, the difference between a population and a statistic. We use Greek letters usually for the population and English letters for the statistic. Okay. And of course, the goal is to use a sample to predict things about the population. And the biggest rule here is the law of large numbers, that as the sample size gets larger and larger and larger, the sample mean, the sample average will get closer and closer to the population mean, the population average, which is why in general, we take larger samples. Here, we see that for small samples, it's all over the place, but once the sample size gets large, it kind of stabilizes at a specific value. That's the law of large numbers. We also learned about the difference between the original distribution, whatever its shape is, and the sampling distribution. The shape of the sampling distribution changes as the number in the sample gets larger and larger. So the population distribution will have some random shape, but the sampling distribution gets more and more normal as the sample size gets larger. Okay, so the population distribution has its shape, and the sampling distribution has its shape. And what we learned about these is the values of the mean and deviation for the sample distribution. X bar is the mean of, suppose X bar is the mean of a simple random sample of size n, where we come from a population whose mean is mu and whose deviation is sigma. The sampling distribution of X bar has the same mean, it's centered at the same location, but the standard deviation is much smaller because it's sharper because of the sample size going up. So it's the original sigma divided by the square root of n. Big concept right here, very big concept right there. So we know that in general, if the original distribution is normal, if it's a bell curve with mean mu and standard deviation sigma, then X bar will also be a bell curve with the same mean, but the distribution will have a deviation over the square root of n, which is exactly what this says here, just described for a normal population. What if it's not normal? Well, if it's not normal, then we have to use the central limit theorem. And the central limit theorem says that, okay, it's okay not to be normal, but if n is big, it's approximately normal. Anyone recall what the if n is big is? Anyone recall what the value of n is for it to be large enough to be allowed to use the central limit theorem as a general rule? I see some texts, and they say the answer is 30. Right, excellent. 3 texts, straight up 30. Once you reach n equals 30, then it's large enough that you can use the central limit theorem. Okay. I mean, it could be valid even less than n, but it's safe to be n. So means of samples are less variable than individuals because they're sharper, and they're more normal than individual observations by the central limit theorem. Okay, and we didn't really do statistical significance. Well, I guess we did in the later sections. Statistical significance means that the result that you got from your sample is far enough away from what you would expect that it's a statistically significant result. If you expect a 10 and you get a million, that is statistically significant, okay? Because you're nowhere close to what you expected. If you expect 10 and you get 10.1, that's not statistically significant because, okay, I'm not going to get 10 exactly, but I'm in the ballpark. So statistically significant results are ones that would not occur often by chance if your expectations are valid. And usually as a result of that, as we saw in the next couple sections in terms of hypothesis testing, if we get a statistically significant result, if we get one that is so far away from what I expect that I have to question my null hypothesis, that's when I reject my null hypothesis. Okay. Okay, so that's it for 15. Are there any questions so far? I know I'm going quickly because I have to leave early, but I'm hoping that as a review, this is making sense. And this will be the first video that I put up on YouTube before all the other videos. So you at least have the review video up. Okay, so then we have confidence intervals. And when it comes to confidence intervals, we know that, or we learn that basically what you have is you have your estimate itself. Your estimate itself is the value that you got from your data, like your sample mean, plus or minus what we call the margin of error, plus or minus a little bit. Okay, and we need a formula for the margin of error, and we have one, as we saw. It depends on z star, which is basically comes from your confidence level. It depends upon sigma, your standard deviation, and it also depends upon your sample size. Okay, and as we saw in the next section, that we have these things, these numbers here, that if your confidence level is 90%, your z star is straight up 1.645. If your confidence level is 95%, your z star is 1.96. And if your confidence level is 99%, your z star is 2.576. You should have your you should have these written down, because those are the 3 big ones that I'm sure, without looking at the test, they're going to appear in the test quite often. But the general formula for the confidence interval for the mean of a normal population is x bar, your sample mean, plus or minus z star, which is what you get from the confidence, times sigma over the square root of n. This is center plus or minus a little bit. So you have this range of values. And you claim with a certain confidence that you believe the mean is somewhere in there. I am 95% confident that the true mean, whatever it is somewhere between these 2 numbers. That's the purpose of a confidence interval. And that's 16. And then we go to 17, which is hypothesis testing. With hypothesis testing, you come along and you say, you know what, up until now, this has been the belief. The mean is 12, the mean is 0, the mean is this, the mean is that. But you either don't believe it or you want to confirm it. So you say, you know what if there's an alternative? What if it's greater than that? What if it's less than that? What if it's not equal to that? And you're testing against the null hypothesis. So you have this alternative hypothesis, and you're testing against the original hypothesis. And you get a result. And then the question is, from that result, what can you conclude about the original idea? Do you keep it? Do you reject it, or do you not reject it? Do you say, you know what, my data does not really support this, so I'm going to go with my alternative? Or you know what, my data does support it, so I'm going to stick with the null hypothesis. Okay, and we had a section on stating the null hypothesis. You pick a value, and then the alternative is either greater than, less than, or not equal to. We talked about that. And then we used crunch it primarily, and you can use crunch it on the exam. We use crunch it to actually compute the p-value of your sample. And essentially what the p-value is how likely it is that you got the result that you got, or something even crazier, if the null hypothesis was really true. If the p-value is small, that means it's very unlikely that you got your result if the null hypothesis is true. And if it's very unlikely that you got your result if the null hypothesis is true, then we're going to reject the null hypothesis. But if the p-value is too big, it's like, okay, it's possible, seems reasonable, or at least it's not out of the blue that I got this, and therefore the result does not make me reject the null hypothesis. So it all comes from the p-value. And we did tests of a population mean. we actually, this is what crunch it is computing. It's essentially getting the z-score of your value that you got, and then checking how likely it is that it's there or past it. You can even do crunch it with that, and it gives you your p-value, which you then compare to the original. And then chapter 18 was about conditions upon when you were allowed to do these rules of interest. It has to be an SRS. It has to be from a normal distribution, and we have to know sigma. Those are the three conditions. Yeah, 8, 15, 16, 8, 15, 16. Sorry, which sections? I just looked at the syllabus a minute ago. Right? What was the? What was the? I just read it to you guys. What was the test on? 8, 15 through 18. All right, 8, 15, 16, 17, 18. 5 chapters. All right, first test was 5 chapters. Second test is 5 chapters. And it's next Tuesday. So it has to satisfy all those. We talked about margin of error not covering all error. It only covers the mathematical errors, but it does not cover the more practical errors like undercoverage or non-response. That would usually widen the margin of error. For significance tests, the question is, how small of a p do you really need? 5% is the standard, but is 5% always accurate? Not always. Depends on the scenario. Okay, and then we also had this section here, which is, what if I know in advance what I want the margin of error to be? How can I work backwards from the margin of error to compute the desirable sample size that I should be going in with? This formula one here is, and you should be writing these formulas down on just a piece of paper. This formula here is what you use. You take your z star, the same z star that we've been using before, you multiply it by sigma, you divide by the margin of error, 0.1, 0.01, whatever it is, you square it, you get a number, and then you raise that number to the next integer. Unless magically you land on a perfect integer, which is nigh on impossible, you round up to the nearest integer after that. And then we also talked about, finally, beta and the power of a test. Alpha, also called the significance level, is the probability of making a type 1 error. Remember, we talked about type 1 errors. We talked about type 2 errors. A type 1 error is an error when the null hypothesis is true and you reject it, right? Because why is it a type 1 error? It's bad. You have to recalibrate, you have to rehire, you have to do lots of stuff possibly because you're making changes. You're rejecting what's been going on until now, even though you shouldn't. If the alternative is true and you reject the null hypothesis, fantastic. If it's true and you don't reject it, fantastic. If the alternative is true but you don't reject it, then you're staying where you were, even though you should be moving. We call that a type 2 error. Alpha is the probability of making a type 1 error. Beta is the probability of making a type 2 error. And the power of a test is 1 minus beta. It's the probability of not making a type 2 error if the alternative is true. We like having high power. High power is good. High power means you didn't do something stupid. Beta is making an error. Alpha is making an error. We want those to be small. Unfortunately, as a general rule, if you lower alpha, you automatically raise beta by going into details that we're not worrying about. The only way to lower them both is by making a larger sample size. But then there's limitations on that, because if the sample size is too much, it's too expensive, or it's not practical. So there's always a trade-off, and that's part of being a statistician, is deciding which part you're going to do and which part you're not going to do to get whatever outcome you want. So when you sum it all up like that, there's really not significantly a lot in this test. Not a lot of calculations, more conceptual, but one of the ones that you really have to know. So power is the probability to not get a type 2 error if the alternative is true. Okay, it's got to be based upon the predicate of the alternative being true. Okay. Know your confidence interval formula. Well, actually, Crunch it will do these for you anyways, but your confidence interval formula, your hypothesis testing formula, the margin of error, the sample size calculation, yeah, I mean, it's just, what was the part about 5%? The general rule is for 5% is, when will we see our new grade on sapling from the last exam? It's on Canvas, your grades, aren't they? I mean, they're on sapling, aren't they? Oh, because I have to raise your grades. Yeah, I got to do that. 7 points, I said, I think it was. Yeah, I got to go in and do that. But the 5% is the general standard for hypothesis testing if you're not given a other value. So if you're not told to use a significance level of 10% or 1% or 2% or something like that, your standard is 5%. And you're comparing the p-value to your cutoff, which is normally 5%. Excuse me. Okay, p being point, not p. No, p is your p-value. P is your p-value. P is what you get from your data. You're comparing p to a value, your cutoff. If p is less than this number, I reject the null hypothesis. If p is greater than this number, I do not reject the null hypothesis. Okay, if you're not given that number, we just take it to be 0.05. But p is from the data, and Crunch it will give it to you. You just got to plug numbers into Crunch it, and I'll pop the number. Yes, you're comparing it to that value. Okay, so be aware of the conditions upon which you're allowed to do these things. What are good types of data collections versus what are bad types of data collections, how to compute a confidence interval and a hypothesis test for your basic situations. And yeah, I mean, that's pretty much it. Parameter versus statistic. Anything involving the population is a parameter. Anything involving the statistic is anything involving the sample is a statistic. Right, so the sample size, statistic. The sample mean, statistic. The sample standard deviation, statistic. The population size, parameter. That's fixed. That's the whole population. Population mean, parameter, etc. On the YouTube videos, can you show how to use Cruncher for these chapters, please? Well, I'm going to put up all the videos. So all the situations that we did on Cruncher, they're all going to be there. You got to search for them. So, but I'm gonna put them up ASAP. I'll try to get them up today, tomorrow, so you have at least a solid weekend to look through them and to go over them, all the chapters. Okay. Yeah, that was a 30-minute speed run, right? Of the last 4 or 5 chapters. So. Yeah, I can't tell you how many times I've watched a video. It's like, feel free to like and subscribe, The game, no, I don't care about. Is it the Dodger game today? Is that game 7? Yeah, I don't care about that too much. But no, I have to do a couple things, and I want to get these videos up, and I want to get. Basically my next class, I'm way behind in their grading, and I needed another hour to do it for them. So don't tell anyone. But we're ending early, so I can do more for my other class, and then maybe one day I'll end early for them, so I can do more for your class. I don't know, but it's your benefit. So thank you. So I will see you guys on Thursday. I'm gonna stop recording now.